All right, so here we go in our last section of this course. We're going to call this 6.12, Volumes of Revolutions Using Elemental Disks and Elemental Washers. So this kind of ends up being a major idea in this course is we have this kind of big theme going on. And we've seen that when we had a function of position. So we had S of t. And if I differentiate S of t, S prime of t, we differentiated that and we got velocity. And so we have a velocity function. If I take the differentiation of that, which is the second derivative of position, then this ends up being equal to acceleration. And so we have this relationship going on that we have these things going in steps. Our units of measuring, this was centimeters. We were measuring perhaps in centimeters per second, and we are measuring acceleration in centimeters per second squared. So the degree of the units is going down by 1 when you're differentiating. When we were integrating, we would integrate velocity to make our position function to be able to figure out what the plus c ends up being. And so that was kind of one of the things that you've seen over the last couple months. Another thing that we've seen is this idea of if we have a function and we differentiate it, that gives us our slope. But if we integrate it, it gives us an area. And that relationship and going back up and down, that interpretation is kind of what we are extending to here. So we're going to get into that. We're just going to start with this function, 3x plus 2. Y is equal to 3x plus 2. And we're going to draw it in this grid. And it's maybe going to go a little bit beyond this grid. And this just ends up being this straight line function. And if we take our area under the curve between 1 and 3, if we have this area between 1 and 3. If we integrate f of x, if we find our integral of f of x, that will give us that area. But what if we start with that area and extend that into another dimension? It's kind of like we have this one-dimensional line, and by integrating it, we've taken it into this two-dimensional area. If we spin that around the x-axis, if we spin that through 3 dimensions and spin that through the third dimension, it's going to intersect this down here, and so we would have this, but it wouldn't just be this trapezoid, it would be the whole 3-dimensional object that we spin out through this around that axis. So we're going to find the volume of this shape. We spin it not just across the axis, but through 3 dimensions. So we'll start with this idea of, okay, so let's take a step back and where did we come from to make this? So when we found this area, we looked at this Riemann sum. And this Riemann sum, all that we were doing is we were taking rectangles or trapezoids that fit under this curve. And the thinner and thinner that we take these trapezoids or rectangles, the closer approximation that our total area ends up being to the true actual area under the curve f of x. And so this was our limit as n goes to infinity. That looked at, as we took infinitely many of these thin rectangular pieces and added and took this area of, this was the height of those rectangles, this was the width of those rectangles, and we're going to add up the area of those. Our notation for this in calculus ends up being this integral from a to b of f of x dx. A is 1 in this case, and b is 3 in this case. The f of x refers to how tall that rectangle is. It infers this. And then the dx is the delta x is the width of this rectangle. And so that ends up summing that up. We're going to use something similar to determine volume of the figure obtained by revolving this area about the x-axis. Our shaded region is known as an elemental. Well, it's an elemental strip is the rectangle. If we're going to rotate that around the axis, what shape would be produced? So we've got three questions here. What shape would be produced? What part of the shape would f of x represent? So the shape that we're producing when we spin it around is called a elemental disk. And so we're going to have a disk. We're also going to refer to it as a cylinder. And it just ends up being this cylinder with varying widths, thicknesses to it. What part of the shape would f of x represent? So f of x, remember, it was the vertical edge of this, and so that height ends up being in the case of our elemental disk. This ends up being the radius of it as we spin it around. This ends up being the radius of our disk. And then what part of the shape would delta x represent? So delta x just ends up being the bottom of this. This ends up being the thickness. The thickness of the disk. You can also think of it as the height. If we're considering it to be a cylinder, it would be the height of that cylinder. So on our next page here, this kind of lays out this diagram. We have this elemental strip here. It has an area, and we're going to spin it around this x-axis. And when we spin it around there, it traces out this cylinder or this disk. The radius ends up being f of x, which ends up just being the height of that point when at x. The thickness of it ends up being, we're going to call it delta x. And so what we have for volume, well, volume of a cylinder is pi r squared times h. So pi r squared, because that's the area of the base of the cylinder, and then pi r squared times h because we're taking that into the third dimension. And so now we have this three-dimensional cylinder. Pi r squared h becomes, actually, it's pi times f of x, because f of x is the radius. So we're going to square f of x. And then when we talk about the height of that, it ends up being delta x. Or when we get to the integral, it's going to be the dx portion. So our volume ends up being the sum of all of these cylinders. So if you think of breaking this apart into a bunch of different cylinders, we have a cylinder here and smaller cylinders, and getting larger cylinders that we are going to stack together. This object ends up looking kind of like this truncated cone. If we stack all of those cylinders together, our volume of it ends up being the sum of all those cylinders from 1 to 3. And our most accurate answer ends up by making each cylinder as thin as we can, or as making delta x, or the width, as small as possible. Which is the same as saying trying to squeeze as many disks into this region as possible. So therefore, we should be taking the integral of this. So for a solid disk, we have our volume is going to be equal to pi times f of x squared, because there's your r squared, and then dx represents the height of the cylinder, or the thickness of the cylinder. So if we end up with this curve that looks like this, well, what we will end up with is this kind of vase or bottle-shaped solid that we're trying to find our volume of. How do we find that? By spinning the area of that curve around the x-axis and adding up all infinitely many areas. Any solid like this is generated forming a circular disk in this way. This formula will apply in all of our cases. Whenever we do a volume of revolution, we're making these disks. So therefore, the volume ends up being the integral of the area times dx. The area is pi r squared. And the dx ends up being the volume ends up being multiplied by the h, the height of that object, and summing them up. So our interpretation here is therefore we get an area by integrating curve. We have this one-dimensional thing, being this line. If we integrate that, we get an area. We get a volume. By integrating. Is the relationship that we have. So in example number 1, determine our volume by revolving or rotating this region under 3x plus 2. So y equals 3x plus 2 is the straight line. We are going to rotate it around this axis from 1 to 3. We want to find the volume of this thing. And as we rotate this around, cross section looks like this, but we rotate it around. We're going to get a thin disk that we're going to generate by rotating around. And each of those thin disks, we stack them together and add them all up, and that gives us our volume. The volume is equal to pi times the integral from 1 to 3 of f of x squared dx. So we're going to take our function, we're going to square it. We can factor that pi outside of the integral because it's just a constant. It has nothing to do with our integration, so we're just going to leave it out here for now. This is 3x plus 2 squared dx. So therefore, integral of 9x squared plus 12x plus 4 dx. And we're now ready to integrate that. This ends up being pi times square bracket 9 times x cubed over 3. 12x squared, add 1 to the exponent, divide by that. 4x to the 1. We've now integrated this, so we don't need the integral sign and the dx anymore, but we do need your limits to integration, so from 1 to 3. All right, so to evaluate from 3 to 1, let's start with when x is 3. So 9/3 is 3 times 3 cubed. 12 over 2 is 6 times 3 squared plus 4 times 3, and that is pi times pi. We are going to subtract. We're going to evaluate at 1. 9 over 3 is 3x cubed, so 3 times 1 cubed plus 12 over 2 is 6 times 1 squared plus 4 times 1, and this is also multiplied by pi. We push this through and we get 81 plus 54 plus 12 pi minus 3 plus 6 plus 4 ends up being 13 pi. And we end up with 147 pi, 8154 plus 12. 147 pi minus 13 pi is 134 cubic units, because this is volume. And number 2. Determine volume generated by revolving and rotating the region under f of x is equal to square root x from 0 to 3. So square root x looks a little bit like this. It goes through 1, 1, goes through 4, comma 2, goes through 9, comma 3. And so it is this curve that comes this way. We are wanting the volume by generating by rotating this about the x-axis. We're spinning this about the x-axis. Our volume will end up being equal to pi times the integral from 0 to 3 of f of x squared dx, which is pi, the integral from 0 to 3. F of x squared is just x dx. So this ends up being the integral x, which is x squared over 2, by pi, and we need to take that from 0 to 3. Ends up being 9 pi over 2 minus 0 pi over 2. So we end up with 9 pi over 2. That is your volume. It's in the shape, it's like a nose cone. And we move on. But question number 3 is going to do something a little bit different. It says, determine the volume generated by rotating between the lines 3x plus 2. So this we've already seen before. So we have this straight linear function, and a line between that and square root x. So here's square root x, and from 1 to 3, it's going to be this. And we are rotating that area around the x-axis to find our volume. Now, what is that going to look like? Well, when we were looking for area between two curves, remember that we took our upper curve and subtracted our lower curve and took the integral of that. This is what we were doing previously when we were wanting to find our area between two curves. We looked at it like that way. Well, this is going to be really quite a similar thing, is that we're going to create a washer out of this. And so this area between these two curves here, when you spin it around the x-axis, it's going to trace out this washer shape, and it's going to trace out that amount. We have the outer radius of this washer, which is going to be 3x plus 2. It's going to be that height f of x. We have the inner radius of this washer, which just ends up being the difference between root x and the x-axis. And when we subtract them, we get this amount. We get this actual height, that thickness of the washer. And when we spin it around, we will get this very thin washer or this ring. How thin is it? Well, that depends on how big delta X is. So our area of the washer is going to be pi r squared of the larger circle minus pi r squared of the smaller radius circle. We subtract it, it's because we're subtracting away that material. So it ends up being pi times the outer radius squared minus pi times the inner radius squared. That ends up being equal to, well, let's call it R2 and R1 for our two radii. This ends up being equal to pi times R2 squared minus 1 squared, just by common factoring pi. And then in the case of our curves up above here, this would be 3x plus 2 all squared minus square root x all squared, which ends up just being equal to x. That's the area of each washer. The volume, therefore, of the washer ends up being the integral of that area, which ends up being pi times the integral of 3x plus 2 squared minus root x squared and dx. Ends up being equal to pi times the integral of 9x squared. I have plus 12x, but I'm going to plus 12x plus 4, and then I'm going to subtract x for the square root of x squared, and this is dx. By the end, this ends up being equal to pi times 9x squared plus 11x plus dx. The volume of our bowl takes that from 0 to 3. So pi going from 0 to 3. We've just simplified this above. This ends up being 9x squared plus 11x plus 4 dx. And then going from 0 to 3, we're going to now integrate that. Ends up being pi times the integral of, this ends up being 9x cubed thirds plus 11x squared over 2 is 4x. This is the integral from 0 to 3. We substitute in 3. This ends up being pi times 9 over 3 is 3 times 3 cubed. This number is different here. 11 halves times 3 squared. 4 times 3. This ends up being pi times 0 because it's 0 thirds plus 0 halves plus 0. So it's just this. So what do we end up with? We end up with pi times 81. 99 over 2 is 12. Putting all those pieces together, 93 times 2 is 186. 99 over 2, getting a common denominator, ends up being 285 pi over 2. So just to fill this blank in, our volume of a desk, this should say washer, sorry. The volume of a washer ends up being pi times 1 of x squared minus f2 of x squared. And that's it. So if you have any questions, please let me know, and good luck.